Hi, everybody. Thank you for hanging around towards the end of the day and taking the time to come and talk about and to listen about cache management. So first things first, it's a tech preview that I will be discussing and talking about today. So we're asking for customers who are interested to join our beta program and be design partners with us. And so what I'm going to be talking about is based on actual customer proof of concepts and beta testing, as well as lots of production workloads that you'll see. But just wanted to be upfront about that. So a little bit about me, Irfan Ahmad. I work for Cache Physics. We're a Bay Area startup, and I'm one of the co-founders. Prior to this, I was at a company called Cloud Physics. As you can see, I have a little bit of a physics envy. And Cloud Physics was using large-scale data processing for IT operations and doing a lot of predictive analytics for helping data centers be run more optimally. It's a SaaS product. It's still around, successful, venture-funded Bay Area company. Before that, I was at VMware for 9 years, worked on the ESX kernel, as well as I/O scheduling and distributed resource management. Originally, I'm from Canada, proud Canadian, and went to the University of Waterloo. Yay! We have a Canuck in the back. And you can follow me at Virtual Irfan on Twitter. Cache Physics, the company, is focused on providing cache monitoring and modeling software. So this is a kind of an interesting thing, cache monitoring. It's a new thing. So really happy to introduce that to you and talk about some very interesting and what I think are very cool details. Overall, the value prop for us is increasing performance and cost efficiency of existing caches, as well as enabling a roadmap to next generation self-managing and self-learning caches. And so, as we've been working with large-scale customers as design partners, we've been hearing cloud-native companies oftentimes running something like 30% of their overall cost for caches. So that's actually really good. That's why you're all here. That's why I'm here, because that's a fast-growing sector, not only in the cloud native now, but also in enterprise. And so that's our singular focus is in making cache management easier and more predictive. So before I talk further detail, I want to set some context. So let's talk about the typical automation journey that teams take. So many of my teams at Cloud Physics, where I was CTO, as well as at VMware, they've gone through this natural journey. You start off with a bunch of scripts and lots of clicking. And so at some point in time, you want to get out of the risks associated with that, and you want to be able to array-file stacks. You want to be able to bring stacks up automatically. And so you go through an automation journey, and if at the end of it you've reached any kind of nirvana, that's you sitting in front of a really nice dashboard. And there's two things about this dashboard. First of all, that having done and completed this automation, you have the ability to visualize and monitor your system. But the other interesting thing that we're going to focus more on is you have lots of dials, knobs, and levers, lots and lots of them. And so what you've really done is you've built this machine that has a lot of levers, and that's a really amazing accomplishment, because once you set those levers, the machine responds. But you still have to know how to set those levers. So at the end of this journey, I think starts a new journey. And that's what I call the post-automation world. And those levers and those dials and knobs on those dashboards, they have to be set to something, and you want to do it intelligently. You want to do it with some goal in mind. You want to do it with keeping costs in mind, right? So which knobs to turn and by how much is what I think is the question that defines this post-automation world. So a question that comes up here is, do we have all the layers already in our systems necessary that we've achieved through this automation journey? So we have automation at the application layer and at the infrastructure layer. Is that enough? Now, some people argue that in fact what you need is you need to slide in a new layer. Okay, and sometimes this is referred to as the systems of intelligence. Oftentimes this is characterized by some notion of needing to self-learn, to model. So what are you trying to model, right? You're slipping this layer in the middle, so you're trying to model the application workloads. How do they behave in production, in reality, not some simulated staging environment, but how are they actually behaving in reality? What can we learn about that in terms of those workloads? And also the infrastructure components, their capabilities. So ideally what you want to do is, in this notion of this systems of intelligence, you want to actually control and operate your infrastructure and your application stacks with some goals in mind: efficiency, performance, SLA conformance, and there are others. Okay, so we are at a Cache conference, and you are listening to a speaker who's from a company called Cache Physics. So we're going to try to translate this into what cache infrastructure could look like under this sort of a model. Okay, so applications stay the same they were in the last slide, but this time we're talking about cache infrastructure at the bottom. So let's assume Redis. Let's assume DRAM. Maybe there's some flash. We heard a lot of exciting things about Redis on flash at this conference. It's very promising. Okay, so if we assume that is our infrastructure, and we're really talking about this concept of this cache infrastructure, how can that be self-learning and self-managing? Well, now let's slip in the topic that I'm really passionate about. And here again, the goal is self-learn, model, auto-tune, auto-adapt. But now we're going to specifically focus on cache components, and we're going to try to control the cache and all of its various parameters and so forth to maximize efficiency, performance, and SLAs. So far, so good? I'm happy to take questions and clarifications as we go. You can object to my characterizations if you like. So caches are critical. They exist in many different layers, whether you're inside a CPU, you're inside a single hard drive or an SSD, or what I've been focusing on a lot lately is application level caches, either against in front of databases or key value stores or in other deployment models. So today, the only insight, and object if you disagree, but the only insight we have about the performance of this cache is this little dashboard. Now, for a given cache, let's just assume 65% hit ratio at the current cache size of 128 gigabytes. So the only number that's available to us that explains and hopefully gives us a window into the performance of this system, of this critical component, is the hit ratio. Okay, so let's talk about this, right? So this is, okay, well at least we have one number, right? But we don't know a lot more about the operations of this system, this critical component. So my claim is, and I'm going to try to prove it throughout the rest of this talk, is that despite the criticality of this subsystem in our infrastructure, intelligent cache management actually is simply non-existent today. It doesn't exist. Now here's why. Okay. So now this 65%, this is a question for you. Is that good performance? Is that good or is it bad? Okay, well maybe it's good, maybe it's not clear. Sounds good, 65%, better than 0, right? Okay, well the corollary of that is, can that performance be improved? If I want to improve the performance of that workload, what will I do? Well, that number doesn't tell me. That 65% number doesn't tell me. Okay, well some of you are thinking, Irfan, come on, you want to improve the performance of the system from 65% hit ratio, you clearly need to add more cache. Well, hold on to that thought because it's not as clear as it sounds. Okay, let's keep going with these questions that I think prove that intelligent cache management today is non-existent, and we'll see how we might be able to go on a journey to figure this out. So how much cache for application A versus B versus C, et cetera, right? There's some trade-offs. Maybe you should give less cache to one, more cache resources to another. What does that mean? How do we decide? Unclear. Today, we don't have good answers to that. What happens if I add or remove DRAM, or if I want to trade off some amount of DRAM with flash? That's a cost question on the trade-offs between those two technologies. But also just thinking plain simple, just DRAM only. Like what would happen if I added more DRAM? What would happen if I removed some DRAM? Would performance get worse or not? Okay, so let's get a bit more ambitious in our questions. What does it take to achieve a 99th percentile latency of, say, 500 microseconds? We don't really have a good way of answering that question. Okay, so now more people are hitting my cache. What if I add more workload or remove some workload? What will that do? Okay. And then perhaps you're an operations team and all these questions seem fancy to you. You just want to know, look, if is there any cache thrashing going on? Is there any pollution going on in this cache that I need to worry about and try to do something about, right? And then finally, what if I change cache parameters? What would happen? We heard in one of the keynotes about a new mechanism being introduced in Redis by the community, which is, hey, we have another cache eviction algorithm now. It's not just LRU, it's going to be LFU as well. Now, how are you going to decide? That's a parameter. How do you decide for that application that's getting 65% whether there's an improvement or not if you change those parameters, right? Okay. So do you guys kind of believe that cache management is basically non-existent? I hope so. So, the title of this talk was about self-learning in caches, and I understand that some of you may have thought I'm going to be talking about machine learning and how to use, let's say, a system like Redis to implement a machine learning stack. Okay, maybe that's what you might have thought. That's not what this is about. This is really about talking about the cache itself and how the cache can become self-learning. So let me try to illustrate that. So you see a point cloud here, and there's 3 parameters, and you see different colors. And so each of the dots in this point cloud represents the optimal cache settings for a single application, and you'll see hundreds of applications presented here. Now, I will give you some examples of those parameters. One of them, for instance, is cache size. One of them we've talked about already, which is LRU versus LFU, so we'll see more. But against some number of parameters, there are many more than 3, right? Each of these applications, its optimal point is different. Now, today, however, how do we set parameters, right? We just do it by some static benchmarking or by rule of thumb, finger in the air sort of a system. So what this is trying to show is that a naive way of setting parameters in your production environments where your caches are running could be leaving a lot of performance on the table or increasing your costs in pretty dramatic ways unnecessarily. Okay. So this notion of a static cache, the one that is configured using static benchmarking or just your previous prior experience, is vulnerable to thrashing, to scan pollution, unfairness, and interference between different components in the client workloads. And then general unpredictability, because you're not sure if you're operating at the right point, and if those points shift, how you're going to respond. Now, whenever you have a situation like this, right, you're operating between these 2 kind of extremes. You can have over-provisioning. You can quadruple the cache. Okay, and just I don't know what the right things are, what the right settings are. I'm just going to throw everything I have at it. Or kind of at the other end, you have just lack of control. Now, sometimes you end up with both, but this lack of control is also problematic. Now, you might try to operate at a better efficiency point, but you end up with this unpredictability and this lack of control. Okay, so let's go back to this dashboard. The 65% example, my challenge to you was of 8 or 9 different questions about that. And what I've done here is just plotted that point on a graph here. So cache size, which is just one of the dimensions we talked about before as a provocative question. Cache size is on the x-axis, and it might be hard to see in the back, but I have just a few different points, 0, 42, 84, 128 gigabytes on the x-axis as cache size. Okay, this again, just one of the dimensions. Actually modeling the system involves many more dimensions. Now, on the y-axis, I've plotted latency. Now, latency and hit ratios are going to be synonymous for the purpose of this talk. They're actually very interchangeable if you know something about the performance of the system that you're monitoring, and I can talk offline with you about how it's just very easy, trivial arithmetic to convert between those 2. So you'll see latency and hit ratio, actually miss ratio on the y-axis interchangeably throughout this talk. Okay, so now we have this dashboard that gives us 65%. All I've done is I've just plotted that 65% on this graph, right? So to be able to answer the questions that we started off with, right, what we need to do is to, my claim is, what we need to do is to learn the performance model of the applications in the cache, and then predict the performance of the workload as a function of the cache size and other parameters. Okay, and I'm only showing cache size here. So what does that mean? Well, we know from calculus a function of something is a plot, right? So we're going to plot this. Now, how that plot was calculated is this modeling activity. And so this is what that plot looks like for an actual production workload that we've looked at. So now let's spend a few seconds looking at this, and I have a couple of slides where I go into detail. So what's happening here is, even though that cache is currently operating at a single point on the x-axis, which is the 128 gigabyte point, the modeling function, or the modeling activity, modeling algorithm, predicted the performance of that workload on any given cache size. So for you to know what the performance of your workload would be at a cache size that's smaller than the current one, you just look it up in this graph. So for example, if you want to know what the performance would be at 10 gigabytes, you just go across and you see there's a bottom of a cliff right at the left there, and that's what the performance would be if you were to reduce the cache size of this workload down to 10 gigabytes. Same thing as the increase. Okay. So now let's look at this. There's a lot of interesting things in this particular curve. So now I'm going to go with the blue dot, and I'm going to say that, let's say, we're going to pretend that the current cache size is 10 gigabytes. So that's approximately where the blue dot is. Okay, so now you're getting some resulting performance from that you can monitor in your system today. But this modeling allowed us to predict forward what would happen. Now let's say that we naively, not knowing this curve, because of a performance trouble ticket that was filed against our team, decided to double the cache size. Now who can tell me what the actual performance improvement would be if you double the cache size? Now doubling is a pretty big function, right? You're going from, say, $100 a day in cache to $200. That's huge, right? Now of course, you know where I'm going to go with this. Quadrupling the cache size doesn't do anything really material. The same thing all the way up to 8x. Now most of us, not knowing this curve, right, because today you don't have that curve, we'll probably give up somewhere between 4 and 8x. Like, okay, come on, the problem is somewhere else, it's not in the cache. I mean, I've gone from $100 a day for this workload to $600 a day. This is not working. What you don't realize is you might be a few cents away from actually getting a huge gain, right? And so this is the power of being able to predict the performance of your system even though you're not operating at those other points, right? Does that make sense? Yes?
So does your modeling assume that the database behind it is scaling linearly, or are there perverse effects where you scale back the cache and then an exponential growth in CPU or other unintended side effects can happen? How do you model that part of the
So there's actually a bunch of things that could happen when you actually make a dramatic change. So let's enumerate, right? For instance, if you go too far to the left, you're going to be climbing a cliff, right? Which means you're going to have more misses, which means your database is going to actually have a much higher amount of traffic that it will receive just over the network, as well as more computation, because now more queries are having to be computed because their results were not cached. Is that a fair? Yeah, okay. So there's at least network, and there is the computational and maybe the disk bandwidth problem with the backend that is seeing more traffic when you go on the left-hand side. And on the right-hand side, it's increases, so, it's a reduction in misses, so maybe we can ignore that for the purpose of answering this question. Is that okay? Okay, so now let's talk about climbing towards the left. So the nice thing about being able to do this sort of prediction is that you can actually argue about how much more traffic the database is actually going to receive. Does that make sense? So because I know that my hit ratio is going to change by a certain amount when I reduce my cache size, I can convert that into the total amount of extra QPS, if you will, that my backend will get. You just straight arithmetic out of the same curve. Now, if you know usually the DBA is involved at this point in time, maybe not the caching team, but the DBA will know the mix, right? And this particular shift in the curve should not change the mix. So now you can just take your existing models for, okay, given the mix, if I get double the QPS going to my actual persistent backend, right, what can I accommodate that in terms of CPU overhead, the CPU headroom that I have, as well as the disk headroom that I have, right? So yes, definitely when you move your system along these curves, there are downstream effects, positive or negative, right? The nice thing is, because this is a model, you're able to deduce from this what those effects will be and then feed them to the other system. Does that make sense? Did I convince you? Okay, great. Okay, so now, yes. Yes, maybe you want to wait for the microphone?
So there's a corollary to that, which is, as I'm walking the curve to the right, the back ends get less load, but the guys ahead of me, north of me, their load goes up.
Yes.
Or at least the load they can serve goes up.
Yes.
And
well, I mean, the latency goes down. The average,
which means that effectively they're doing more operations per second, which means they'll hit a new bottleneck.
Well, so it depends upon whether they're backlogged or not. So if we make the assumption that they're backlogged, so if they're not backlogged, then the bottleneck might disappear and you just get pure improvement in latency and throughput just maxes up because you're not backlogged. But sorry, backlogged is a term which basically means, are you assuming like infinite load? Like if the more performance you do, the more load comes in? Or internet systems usually are not fully backlogged, right? There are some periods that look like they're backlogged, but usually not. So that's something we'd have to reason through. But yes, the upstream will have the ability to serve more and will become the bottleneck.
So maybe the way to point is, since you agree with that effect, how far do I connect this to the services that are calling into a caching layer?
Good question.
Because I might say, look, I increase the cache by 10x because that's where the next cliff is.
Yes.
But in fact, I'm not actually getting any net improvement in the system.
Right.
Because I was only a few QPS away from pegging the front end. Right.
Okay, that's a good question. I think you'll agree that the answer is similar to the answer that I provided, which is on the downstream side. The fact that we can argue about and reason about the performance improvement that we're seeing by increasing the cache size to a certain amount allows us to reverse feed that computation up to the higher layer so that that team can go and actually adjust it and see how much headroom they have.
That's the part where your model here stops.
So my model would feed the higher layers model. Yeah. And the other quick thing to mention is that, and I can show you offline how to do this, you can actually generate a throughput curve from this, not just a latency curve. Okay, so there's a equivalent to this that I'm not showing in this talk, but there is actually a similar computation to generate a throughput curve. And when you think about the throughput curve, then your question and your comment, I think both become a little bit easier because now you're dealing with the same units of what that team might be operating with, right? And with latency, you have to kind of do a little bit of a mental shift to say, well, what does latency mean in terms of throughput? But there is another curve just like this one that is throughput. Does that make sense? Okay, so what I showed here was that, remember, we don't know this curve today, right? But if we knew this curve, then we can actually skip all this experimentation and kind of go to where the right operating point is that we desire. Let's look at another example. So in this example, I'm currently operating wherever that is about 80-ish gigs, right? And if you think about it for a minute, it's like that's actually a really bad operating point for that cache because it's inefficient. So why is it inefficient? Well, you've actually burnt a lot of cache during that flat region. That's the thrashing region, right? Before the 80 gig, between 10 and 80 gigs, you've already invested the dollars. You haven't got any benefit. So maybe you're better off actually shrinking the size of this cache and using those resources, either saving money or using those resources for some other application that actually needs to grow its cache so that it can end up on the other side of a cliff and actually get a huge performance improvement, right? The other thing that we get out of this sort of analysis is that we get to identify all those cliff points, okay, and feed them into our systems, either automation or monitoring systems, to say, okay, well, whenever you want to figure out, want to fix a performance issue or do capacity planning, right, these are the points that you want to be sitting at, which is always at the bottom of a cliff, at the start of a flat region. Does that make sense? Yeah? Okay. So far, hopefully you've fallen in love with this curve for this particular workload. I've talked about it ad nauseum. So let's introduce a different, a bit of a mix of curves. So these are from some production storage workloads. By production, I mean these customers and several different customers' workloads are represented here. But this is what your dashboard could look like. Although, as I said, I've picked from different customers in this case. But these are running their real production environments. There's OLTP, there's mail server, there's analytics workloads in here. But the reason why I give you this much eye candy is that we get to see the diversity of those shapes. Okay. And now we've started to get some skills associated with how to analyze these. So whenever you see a flat region, you know there's some thrashing going on. And you don't want to operate on that flat region, right? Because there are some workloads. Let's look at a couple of them. So I'm going to highlight in green this workload, which is T09. And we had to obfuscate, obviously, the actual customer names and the workload names and so on. But if we look at T09, you'll see a more or less flat region and then a cliff, a single cliff at the end, right? Now, it's hard to see from the back, but on the x-axis, you see 120 gigabytes as the point where the cliff happens. Okay? So this is actually a pretty serious, large single workload that is behaving like this. Think of it as a working set that's not fitting yet until you get to 120 gigs and it fits. So this is that example, single big working set. Okay? Another one we want to look at, this red one here, that there is actually a single cliff, and you get almost all of the benefit between 0 and maybe 10 gigabytes. And any extra resources that you give it, they are going to improve. So because there is a gentle slope, okay, of improvement all the way to 400 gigabytes. But if you were to do this analysis, let's say over a few days, and just say, hey, how many keys were accessed? 400 gigabytes worth of keys were accessed, right? But the benefit was only in the first 10 gigs worth of keys. So this is the sort of insight you get once you start to internalize the opportunity that these curves provide, these models provide. Now, the final one I'm going to look at, this blue one, is T20. And in that case, you'll see that there is a gradual performance improvement. In a way, we all wish every workload was like this one, because you feed it some resources and it gets better. You feed it more resources, it gets better, and that's become a relatively linear function. The reality is that not all workloads behave like this. In fact, many, many don't. And so this kind of more or less randomly selected set of models goes to illustrate that there's no single rule of thumb that's going to work here, right? Inside your environment, you might be running multiple Redis databases or other caches and might have dozens of different workloads. I guarantee you no two look alike. And so therefore, no two can be operated in the same sort of way if you want to worry about performance efficiency or SLAs. Make sense? There was a question in the back.
Throw it.
Hello. Yeah, are those workloads, is all that behavior largely independent of the cache replacement policy and regions?
That's a great question. So I had talked a little bit about cache replacement policy. I had mentioned that, for example, if you wanted to distinguish between the performance available using LRU versus LFU, that you could use this model. All of these curves are actually LRU because those are the systems underneath that we were simulating. Okay?
Right, but you can't automatically discover
all of these, if you were to rerun our analysis and say, hey, this time run with LFU, they all look different. And some of the ones that perform poorly, with lots of resources might all of a sudden start performing much better. So it's literally changing cache replacement policy has a dramatic impact, which is not easy to predict by just looking at the LRU curves compared to the LFU curves, for example.
Right, but you can't infer different regions and which data belongs to which region.
Sometimes, sometimes not. So there are times where you see a curve that's really flat and then down, so that's the thrashing workload, and then with a different cache replacement algorithm, it goes straight across the diagonal. So the differences are absolutely humongous.
Okay, thanks.
You're welcome. Okay, so now, so I think we've gotten some comfort with these models and the shape of these curves. Again, I'm only focused right now on a single slice of this, which is cache size. But now what we're going to do is, now that we have some familiarity with this new tool that we've learned about, we're going to start to apply it. So the first thing I'm going to apply this to is how to achieve latency targets. So now let's say there's a client or an application owner that comes to you and says, look, I need a 7 millisecond latency target for this particular workload, this particular application. Oh, and by the way, it's not just a average latency. It's a 95th percentile latency target. You cannot violate that. 95th percentile, 7 milliseconds. Suppose that's something that is required of you. So the way we're going to use this new tool, these curves, is we're going to say, okay, well, we already have latency on the y-axis. And what I did was I converted the average latency that you saw in the previous slides into 95th percentile latency. Again, it's just plain arithmetic. And it's trivial to do the transformation. All you need to know is what is the actual 95th percentile latency, and it's just arithmetic after that. And many systems today are not just tracking average latency already, but also tracking different percentiles. So whichever percentile you're interested in, you actually measure that in the real system, plug it in here. And now what we do is this trivial thing, which is, okay, you said 7 milliseconds? Well, I know where 7 milliseconds is on the y-axis. Let me draw a line that goes all the way across, and when that line intersects my curve, I know that I can size my cache to that amount, and I am guaranteed to achieve that latency. Okay, now, some of you know me from my past careers. I've spent a good portion of my career looking for a system that can guarantee latency, and there's a corollary of this, which is about throughput. I've tried so many different techniques using placement, using I/O scheduling, and when our team figured this out, right, that was like, I felt in a way, I don't know if I'm going to top myself in terms of achievement here, because this is absolutely a crowning achievement of the team to figure out how to do this. Again, all based on the curve, all based on this model that predicts what the latency would be under different conditions, and all we did was just interpolate. Okay, so in this particular case, the model says, look, if you want to get a 95th percentile latency of 7 milliseconds, you need 16 gigabytes of cache. And if I was you, I'd add a little bit more in case the workload changes a little bit. So maybe you go with 18 or 20, and now you're pretty safe with your workload SLA. What do you guys think? Interesting? Yeah? Okay. Okay, so we're getting some familiarity with this tool, so now I'm going to push it a little harder. We talked about 95th percentile latency targets, and of course that's just an example, could be 75th or 99th, whatever it is. Okay, so now we're going to go and do this thing, which is very challenging, which is, look, I've got multiple tiers. Now, in the world of Redis, this is new with Redis Flash. In other environments, tiers are very common and required because the amount of data, the size of the data set that you're dealing with is so large, you cannot just store all of it in your cache. And so you have to tier, or your DRAM, let's say, right? And so you have to tier. And as you think about, this was talked about earlier today, as you think about roadmaps around things like 3D Crosspoint and MRAM and STT technology, that you're going to end up with DRAM, like honest to goodness DRAM, and then you're going to end up with this thing that's a little bit slower than DRAM, and then you're going to end up with this thing that's like Flash and NVMe, and now we've got tiers, and we've got to figure out, look, how much of what do I get? And this is one of the questions we asked at the beginning, right? How do we figure this out? How do we know? How do we predict ahead before we go and buy the hardware or buy the resources and just experiment? So now in this case, what we've done is we already have this model, so what we're going to ask the model, something a bit more complicated than last time, is we're going to say, dear model, tell me what is the best operating point for me if I have 3 tiers. And I put into the model the latency profile of misses with that tier. Okay, so with DRAM, it's, let's say, hits, and then a miss of DRAM ends up in the second tier, let's say it's SSD or some NVMe device. And then there's a network cost going across a network for yet another little slower layer, right? So we input into the model the missed latencies for each of these tiers, and what it pops out is those partitions. So what it says is that, look, given the performance characteristics of this workload and this cache, you should put a certain number of gigabytes in DRAM and a certain number of gigabytes in flash, and so on and so forth, and that is your optimal operating point for whatever target you set. You can even use this to set SLAs, once again, because you can just reason through arithmetically what the latencies are, and you can hit your 7 millisecond from the last example, but this time do it with multiple tiers. Okay? So again, once you have the model, all we did is we said, well, what portion of this curve should live, what portion of the activity of this workload should live in DRAM versus flash? So if we keep going with this, and this goes back to the question that I think Steve asked in the back, which was, well, what about this LFU versus LRU versus other cache algorithms? What about that? So what I'm showing here is a single workload. I know you see many curves here, but trust me, it's a single workload, and the only difference between these performance models is that they were built assuming different cache policies. Okay. So now, as you can see, in some cases, a certain cache policy is much better than others, depending upon what regime you're operating in. So the same tool, and all we did was we just reran that and simultaneously ran multiple different cache assumptions, okay, using that modeling system. Okay, so we talked as a corollary to the previous argument, which says, hey, tiering is something that's interesting. I think what we're seeing is that the total amount of data that folks want to store in faster tiers than disk is starting to grow dramatically. And now we're seeing enterprise adoption of application-level caches for things like Memcache, things like Redis. And so this opens up a lot of very interesting and important questions. If we're going to store more data at those layers, right, cost does become an issue. You cannot store, hundreds of terabytes very easily without breaking budgets, at least for some organizations. So what I did was I just plotted latency SLAs. So what is the hard SLAs on the y-axis with cost sensitivity on the x-axis, and the most cost sensitive are the yellows, and then it reduces from there. And so high frequency trading, of course, you have to have very strong SLAs for very, very tight latencies, and then you're not that cost sensitive. Cost sensitivity increases all the way out to decision support systems. And so this is where tiering, we think, is going to start to become much, much more interesting. We're really happy to see this particular community move towards that in haste. But again, these are questions that have to be answered systematically, right? Which apps need that microsecond latency that you get, that the HFT communities need? And of course, at least recently when I checked prices, you still have at enterprise class, 10x per gigabyte for DRAM compared to flash. So now there's a huge opportunity there to fit larger working sets when it's not necessary to have everything run in DRAM. And then, of course, there's this analysis that we all have to do, which is, where is the bottleneck? Where's the actual bottleneck, right? And so, for example, sometimes network latencies can dominate. And so if you're serving traffic from San Francisco to New York, your network round trip is going to be 150 to 170, something like that, milliseconds. So adding another 1 millisecond of latency from an NVMe device that can save you 10x in cost might be something really smart to do. Whereas if you're dealing with a system that is in between two machines in the same server room floor, right? Okay, well, DRAM actually might make more sense there. So as we look forward and kind of focus on Redis, right, so we see deployments that are RAM only predominantly today. We think that will start to change as the best practices for how to have tiered system and hybrid systems come into play, will improve, and so as that know-how and as those best practices get established, I think we'll see a combination across tiers, and I think that will just become normal. I think in a couple of years when we come back to this conference, right, I think these things will start to become very normal. But again, the questions about how much RAM, what policies make sense in these tiered environments, and how much flash am I really looking at? Those types of questions will become even more important than they are today. Okay, so I'm starting to come to a close. I wanted to talk about, what is this journey towards these systems of intelligence that I started with and made some claims around at the beginning. And so where those are concerned with caching, I think that the first step in that journey is towards monitoring. Being able to have a dashboard, right? Isn't it time that we had a proper dashboard that actually gave us insights for the caches that we operate? So that's, I think, the first step in that journey. Next, I think, is this notion of auto-selection of policies. And for the Redis community, this is going to become very real very fast. There are some workloads that you really want to operate with LFU, some with LRU, and how are we going to figure that out, right? Then we talked about latency guarantees, and I think, again, increasingly as the know-how in the community increases around this, right, best practices, unfortunately, are not going to be enough to really get to hard latency or throughput guarantees in terms of QPS or milliseconds. Accurate tiering, I think, once again, we meet in a few years. I think this is going to be a huge, huge concern, and that's part of the journey towards these self-learning caches. Now, one thing I didn't talk about is latency reduction. So anytime you have those flat regions in those models, there are actually some neat tricks that we've discovered, which can actually, just by tweaking the cache a little bit, you can actually drive to the what is the convex hull of those flat regions. So this ends up being massive improvements in efficiency, because for the same performance, you can actually run much smaller caches to be able to get to that performance. So happy to talk about that offline. And the other thing we didn't talk about today is multi-tenant isolation. If you start to end up in situations where you have multiple tenants, well, how do you manage that? How do you make sure no tenant is thrashing another tenant? So the result of all of this, we're really excited in terms of the ability to simulate, the ability to look ahead and predict, and so that you can safely quantify the impact of changes without actually making them in production, so you can move with confidence. Furthermore, the efficiency of caches being improved. Often we see 50 to 150% improvement in the cost efficiency. We talked about latency SLAs. We've talked about the concept of being able to improve consolidation ratios and more accurate capacity planning. So I'd like to end with, of course, thanking you for taking your time today, and also an appeal that we're interested in working with customers in our beta program that I talked about in this tech preview today. Please follow us on Twitter, and I'm happy to take a couple questions. Thank you. There's also one in the back. Hey.
So one of the difficulties about these systems is I have to actually run at least one experiment at one data point, and you map the curve. But the number of permutations on knobs, I mean, moving capacities is an easy thing, but the number of software knobs and policy knobs makes the test matrix go exponential.
Yeah, and that's the brilliance. Thank you for making that point, because that's the brilliance of doing it in a using a modeling system, because you do nothing to your production environment. Literally, our system will come in, will sniff the traffic in a very lightweight way, and using just that sniffing of the traffic, think about it, 0.1% sampling is our default sampling rate. So if you have 1,000 keys going by your system, we're only going to study one of those 1,000 keys. That's enough for us to be able to model, dozens of different configurations, dozens of different cache sizes, different policies, et cetera, all of that happening completely online in parallel. You don't actually have to do any experiments at all. You just run your production as is, plug the system in, and keep going.
So clearly your secret sauce is the model that allows you to predict what the latency would be. And obviously, I'm not going to ask you to explain the secret sauce. But the question I have is the latency. Now, latency as a response time would be a function of how the backends are working and how much they're thrashing, your databases and so on.
Sure. But
in this case, you are equating latency with just cache miss. Is that
so
correct?
what we're saying is in the model, what we look at is what is the hit latency and what is the missed latency at that cache level. So the missed latency includes all of the computation that the database has to do, all the disk scans that it has to do, and we get the whole percentile of that, right? And then the hit latency is generally like flat because it's DRAM, right? Or it's flash. So we're taking both into account for those curves. Does that answer your question?
I see. So you are sampling the traffic. You're looking at,
Yes.
what kind of response times you're getting at a point in time, right? You're not changing the backend configuration.
No,
you're not
we're not
adding
changing.
more servers. You're just looking at how
That's right.
the system is behaving as of now
Yes.
with the current cache, whatever the cache may be.
Yes.
And from that, you're able to create a model that could predict.
So we just look at the workload. We don't even look at the cache settings right now because we want to not simulate just the cache that you're
Of
running.
course.
We want to simulate all possible cache sizes, many
Right.
different configurations. So we try not to be bound by what's currently running. We look at it more abstractly and model lots of things in parallel.
Interesting.
Okay, thank you. Maybe one last question up here.
Yeah, good presentation.
Thank you.
Quick question. When this, trying to go to the fundamental thesis of it, like,
Yes.
this is all good, when there is kind of a good affinity between the apps and the physical resources. What happens, when the apps are like highly mobile and the affinity is actually pretty much broken?
So a classic example of that is multi-tenancy. So single cache is addressing workloads from different tenants. And so I'm just abstracting away whether it's mobile or not, or different apps, whatever. Let's just say there are multiple tenants, right? So when there's multi-tenancy going on, right, those tenants are going to fight against each other. Some tenants are going to throw workloads of the other ones out. And so that's one of the things that I mentioned, but I didn't go into deeply. We can discuss offline. But in that case, what you need to do is you just need to tag our algorithm's input with the client ID. And all of a sudden, it will start to model all possible clients separately and then combine them to figure out what relative sizes should be, et cetera. Okay? Well, thank you very much. I really appreciate the time. Okay.